Hey everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 5 of Rectifiers chapter, right? So we have studied a lot. We have studied about half of rectifiers with complete RLE load. In this lecture we'll study about a new term known as freewheeling diode and why is it used and like why do we need it and why is it used like as shown, okay, as shown, like why is it used as shown, like what is the reasoning behind using this. So all those things we'll learn conceptually. Then we'll obviously do few questions and have a rectifiers with freewheeling diode, and I won't be able to cover the capacitive filter in this lecture. In the next lecture I will give you a few homework questions, and in the next lecture I will solve those questions that I gave you homework, and we'll understand the concept of capacitive filters, and also if our load is capacitive, right, then what happens, that also we'll understand. Okay, so these are the things that we'll understand now. So first of all, let's start with freewheeling diode. So freewheeling diode is a low switching frequency power diode like SCR. So just it is a diode. Instead of SCR, we use a diode across the load. Now why do we use it? We use it to make the output voltage 0 when the input voltage is negative. What do I mean by that? So basically I have a RLE load, right? So freewheeling diode is only used with loads which have inductance in it, right? Which has some inductance. So here what happens when we saw the analysis of like inductive loads, right? What was happening there was that whenever I had inductance, the inductance was keeping the SCR on even when the supply voltage was negative. When the supply voltage was going negative. So what was happening? My output voltage was becoming negative, okay, for certain amount of time, and my overall power was reducing actually. Even though the current, like continuity of the current, conduction current is like conduction of the current or continuity of the current conduction was increased, but the overall power was reducing because the voltage, output voltage was becoming negative. So overall average power over a cycle was reducing. Average voltage also was reducing, just that I just explained in my previous lecture itself. Why was average voltage decreasing? Because obviously the voltage, right, was going negative for some point of time, and I don't want that. I don't want that to happen. For that reason, I am using freewheeling diode to stop that. Like what does freewheeling diode does? It helps to keep the conduction alive. Also, it helps in keeping the output voltage 0 by keeping the conduction alive. Okay, it does two things at once. Previously, I was losing out on something. Either I was losing out on conduction or I was losing out on output voltage, average output voltage. Now, with the help of freewheeling diode, I am not losing out on anything. Is there any drawbacks? All those things we'll understand. So this conducts based on load conditions, which causes it to freewheel. So this, right, freewheeling diode mainly conducts based on the load condition, not on the supply condition. Okay, when we will do the analysis, there we will understand. Freewheeling diode conducts due to charge inductor of the load. It never conducts in resistive or RE load, because resistive, simple pure resistor or RE load does not have the capacity to change its own voltage so that it can turn on the freewheeling diode to keep the conduction alive. They don't have that capability. Only inductor has it capability. Why does it have the capability? Because it can store energy. It can store the energy, right? Our resistive load can only dissipate. Okay, like RE load can only E load, like battery can also store the energy, but battery cannot change its voltage, right? Battery can never change its voltage, but inductor can change its voltage. So all those things are there. That's why. So freewheeling diode, first of all, whenever you see freewheeling diode, the load must be RL, RLE or LEL, inductive, right? If the load isn't inductive, right, it doesn't matter if the freewheeling diode is present or not. It won't do anything. Without the freewheeling diode, with the freewheeling diode, nothing will be different. Now let's start with the functionality. In any AC to DC converter, single phase half wave, it operates in two quadrants. Like like the freewheeling diode operates in two quadrants, prevents power flow from load to source, ensuring electrical braking mode does not counteract. So this, right, whenever we use electrical braking in DC machines, we will study about this. So what can happen is, whenever we are using electrical braking, if the speed of the motor is very high, right, it can supply the power from the motor to the supply side. To the supply side from where we were taking the input, right, and opposite end from, like, current can flow in the opposite direction, that can damage the system. Okay, so this freewheeling diode actually prevents that. Okay, that this we'll understand in the machines chapter. Okay, like how does power flow from load to source while electrical braking, all those things we'll understand there. It is essential for continuous operation in half wave rectifier. So I told, right, it is impossible without, like, we haven't studied freewheeling diode in the previous lectures. So I told you it is impossible to get continuous conduction with just half a rectifier. But if a half a rectifier has a freewheeling diode with it, then it is possible that we will be able to get continuous conduction of load current. Okay, continuous conduction of load current. Advantages: average value of the output current increases because the current is more continuous. Average value of voltage increases because why? Because the VO can never be negative. Previously VO was going negative. VO can never be negative. Okay. Next, this reduces ripple in the output because the continuity of the current increases, and hence like current won't go to zero that for that amount of time. Hence it reduces ripples. That also we'll understand. Like this mainly happens with the filters. This is effective mainly with the filters. Efficiency of converter increases. Why? Because my VO increases, right? My VO. Just hold on. Okay, this VO increases. As my VO increases, obviously my output power will increase, right? And due to that reason, VO average increases. So improves power factor. Again, why does it improve power factor? Because my power improves. So like, and what is power factor? It is PS upon SS, and if the converter is ideal, it will be PO upon SS. Hence PO will increase, and hence the power factor will also improve, right? So everything will be good with freewheeling diode. So obviously we use it. Now let's go for the disadvantages, right? So every good thing has its own disadvantages as well. Like obviously, then why don't we always use it? So obviously this has disadvantages, but the advantages actually is too good to not use it, right? So here at application of freewheeling diode is good up to moderate power rating converters. So if the rating of the converter is very high, right? So diode cannot, like that diode whatever is present, that won't be able to handle that amount of high power rating. So the diode can get damaged, and we don't use that because at those high power sides something else, some other problems may arise. That's why we don't use it. Next, switching problems increases. Why? Because like there are two devices now. One is this switch SCR, and then there is a diode. So obviously the complexity will increase. Then continuity of load current still depends on the load components RNL. So even though we have reduced the dependency on the input voltage, okay, it doesn't depend like our IO, right? IO doesn't depend on our input voltage, but our IO does depend on RNL. How? It depends on the time constant, right? It depends on the time constant. Tau is equals to L by R. So if my L is very, very high, that is my L is very, very high than R, then, okay, no, not this. If L is, yeah, am I correct? Yeah, if I'm correct, if L is very, very high than R, then it will take more time to discharge. So it won't discharge throughout the whole circuit. It won't discharge throughout the whole circuit. That is not this, not L very, very high than large. Basically, L by R must be very, very, very large than the T by 2. So because why? Because during the first positive half cycle, my output voltage is anyways positive, so that this diode won't come into the action. Okay, when the output voltage is, or when the input voltage is negative during the second half cycle, then this freewheeling diode will come into action, and then only here, right, if there is RL load, whatever the energy that inverter has, that will discharge through this freewheeling diode. Now if my time constant is very, very high, so the time to completely discharge will be very, very long in this complete half cycle. Okay, so yeah, this is basically my time constant and all those things. Okay, so let's do the analysis. There also we'll understand this better manner. So here, right, first, a single phase half wave rectifier with freewheeling diode with RLE load. So like here, what we'll do, we'll take one assumption. Like all these things we know, the assumption is my load current will be in continuous conduction mode, and if my like time constant of this load, right, if very, very large than the time period, then I can assume it as constant as well. Once we'll analyze, there we'll understand. So many things will be same, but few things will be different. Case one is basically from alpha to pi, because before that, right, diode won't conduct, diode will be off. Okay, so from alpha to pi, I'm assuming that at omega t equals to alpha, SCR is triggered. SCR is triggered. Okay, so if SCR is triggered, then the SCR is turned on. If the SCR is turned on, that means what? That means that current will start to flow. And what is the voltage? What is the diode voltage? Diode voltage VD is equals to minus VS, right? VD equals to minus VS. And what do I know about VS? VS in this region, right? In this region, omega t between alpha to pi, I know that my VS will be positive. VS will be positive. Hence, this thing will be negative, right? Because VD will be negative and VD is negative. So, this diode is off. This diode is off. And then the circuit will work as it is as we are analyzing it previously. From alpha to pi, it will work as it is as we are analyzing it previously. Now, like here, like what are the analysis? The analysis is basically my current will flow through the SCR. So, my IS will be, this time my IS will be equals to, IO will be equals to IT. Okay, all this will be equal and it will be positive greater than 0. And obviously my ID will be 0, right? Why? Because this diode is off. So here, right, diode is off. Okay, diode is off. Now what next? What is next? So next thing is that how will the power flow? How will the power flow work like? So the power flow, right? Power flow will be from source to load because current is positive and my voltage is also positive. Supply voltage is also positive. So current will flow from source to load. So this is source and this is load, and like current as like not current, sorry, power, flow of power, right, will be from source to load. And what do I know? So the inductor, right, will be energizing now because it is like it is energizing because the power is flowing from source to load. So obviously the power will flow through the power will be stored in the inductor as well. It will be dissipated in the resistor and battery, but it will be stored in the inductor as well. So my like VL will be positive, okay, and my DIL by dt will be greater than 0. And obviously if my DIL by dt is greater than 0, that means my IL is increasing. My IL is increasing, right? So this is one thing. Now like all these equations will be valid, right? What are these equations? This equation I derived during the that analysis of RL load. Okay, all these equations are same and these are valid only. Now this will be the equation of the current. Okay, and if my R by L is very like if my L by R, what can I say is that if my L by R is very very high than T by 2, right? What can I assume? That this number, right? This number, okay, this number L by R is very very high. That means that just hold on, T upon tau. Okay, so this I can write it like this. Okay, that will be easier for me to analyze. By R. Okay, so this is very very higher than T by 2, right? So this is very very, this will be almost be equals to 0, e raised to power 0. I'm making some mistake over here. Okay, no, this is for the discharging period, right? Okay, this value will still be there. There won't be any transient because this value will be constant. Okay, if L by R is very very large than the time, right? So let's say this T is very very, like T is very very small than this L by R. So what will happen? This will be almost equals to 0. This will be almost equals to 0. So there won't be any transients. Why? Because this will be almost like e raised to power 0 is simply 1. So like the current will be this sinusoid response and of subtraction of this constant term, because at omega t equals to alpha, current is 0. That's why, right? So all these things that we already know. Now let's understand this load by load. So for basically RLE load, right? RLE load, that this pi minus theta factor is also very important to us. So from pi minus theta to pi, what will happen? My VS will be less than E, right? From pi minus 0 to pi. But one important thing is my VS is still positive. If my VS is positive, and what is my VD? And SCR is still on, right? SCR is still on. VD will be simply minus VS. So hence diode will be still off. Diode still off. Even though this is RL or RLE, the outcome will be same. I will explain for RL as well. Diode still off. So for RL, right? and RL and RLE everything will be same. Okay, so for RLE this was just an extra analysis, but for RL this will be off till pi only. This diode will be off till pi only. There is no confusion in this. But for RLE there might be a few confusion, but still this diode will be off because my supply is still positive and VD is directly negative of this. That's why. Now here, right, in RL load, if from pi to beta, what will happen? From pi to beta, if the load is RL, then this SCR, okay, as soon as this SCR is closed, because inductor will try to keep the current flowing and this diode is still off, right? So inductor will still make this SCR on, and as soon as at pi plus, at omega t equals to pi plus, what will happen? Omega t equals to pi plus, basically my Vs, my Vd, right? Vd is what? Minus Vs, and my Vs is what? Very small, but just negative, so my Vd will be just positive, and I am assuming diode as idle, so Vd just become positive. The diode turns on. Diode turns on. Okay, the diode turns on. So what will happen? As soon as the diode turns on, right, as soon as the diode turns on, so this will turn off. Why will this turn off? Because both of this cannot be on at the same time, because KVL will not be satisfied. KVL will not satisfy. So if both of them are on, right, if both of them are on, then you can write this as what? Vs is equals to Vt plus Vd. So both of them cannot turn on. Why? Because Vs equals to Vt plus Vd, and if both of them are on, this is 0 and Vs equals 0. Vs, I cannot fix Vs to 0, right? That is not possible. KVL will not be satisfied. So obviously this inductor will keep only this diode on, and this diode will be automatically turned off. Sorry, not diode, this SCR will be automatically turned off. That is, SCR will get naturally commutated. SCR will get naturally commutated. Okay, SCR will get naturally commutated. So this is what that will happen. Now as soon as this SCR is naturally commutated, this inductor, this is simply like a RL circuit. It is simply like RL circuit. What circuit is this exactly? If you have studied transient very well, you will be able to say this is a source free RL network. Okay, source free RL network. So here, right, what condition needs to be followed? So if this is source free RL network, I can draw the network, redraw the network like this. This is R, and here, right, this inductor has some current. What is this current? That is IO max. Okay, because for a RL load, it energizes till pi, omega t equals to pi. So this is IO max and this is some R, right? And obviously this has some inductance as well. And simply, what is the equation? The equation is simply this discharge equation for this. Now my IO of t, right? IO of t will become simply this IO max e raised to power minus t upon tau. Okay, and what is my tau? Tau is L by R. Now if my L by R is very, or I can say if my 4 tau is very large than t, right, is very large than t by 2, okay, then this tau will be very large than normal time period. So how much time window I have? T by 2, half cycle, right? Then again in the next half cycle, this SCR will turn on, and again this will energize the inductor. So current will increase again. So the current decreases for on the t by 2 period, and this t by 2, if this 4 tau is very large, this will be almost equals to 1, because this will be e raised to power minus 0 almost. This will be on 1, and I of t will almost be constant. I of t will almost be constant. Okay, so from this condition only we can understand that how my inductor current is getting constant due to this condition. Okay, so basically this is the waveform for a RL circuit. For a RL circuit, write it here. And this is the supply voltage, and if like this is tau 1 is less than tau 2 is less than tau 3. Okay, basically the inductance is lower than the second one, lower than third one. So as the inductance is lower, so it is discharging and discharging more. Okay, the current has more ripples. So this, right, as the time constant is lower, I am getting more ripples in the current waveform, more ripples. And here, right, as my time constant is getting more high, I'm getting less ripples. So that's how it reduces ripples as well. I'll show you here, right? If you see here, the time constant is very high. So like during the discharge period, right, here until here it was charging fine. During the discharge period, what will happen? The time rate is very high than the time constant, so it will discharge by very low amount. It will be almost equals to my IO max. It will be almost equals to my IO max. Okay, this is not the voltage waveform. This is the current waveform, right? Not the VO. This is the current waveform. So this value, right? I can name these values. So this has some particular value. What is this value? This is at pi, right? So this is at pi. So obviously at pi, the equation of the current I have already derived. You put omega t equals to pi, and that will give you as the maximum current, IO max. So here this will discharge very low amount. Again, it will charge after this 2 pi plus alpha. This will discharge till from pi to 2 pi plus alpha. Then again it will charge, and then again it will discharge, but very low amount, because my time constant is very high. It will take very large number of it will take very high number of time to totally discharge. Okay, so that is the reason. So for continuous current, right? So if I want my current like this, absolutely ripple free, what are the conditions? The conditions are that load inductance must be very high. That's why we always say the inductance is very high. Why do we say it? Inductance is very high, so that the time constant is very high, so that the time it requires to discharge is very high. So it doesn't discharge by much, it discharges by very less number, because this, right, if this is very small number, I can linearize this, and this will be just a linear function. All this I have explained in my pulse response video as well. Okay, so these are the few conditions. Minimum conduction period of the diode must be pi to 2 pi plus alpha. So like these are the conditions that, like, that this freewheeling diode, minimum conduction period of freewheeling diode must be pi to 2 pi plus alpha. It must be pi to 2 pi plus alpha. It cannot be lower than that. Okay, it cannot be lower than that. So these are the few things we see. If for some reason it is lower than this, that means my inductor has fully discharged. So this diode is also not conducting, and this rectifier, SCR is also not conducting, right? So inductor has fully discharged, current has become zero. When the current becomes zero, this diode is not on anymore, this diode is off. So these are the few things. Now here let's understand with simple RLE load. Okay, and if the current is constant with RLE load and the IO is constant. So if IO is constant, right, from alpha to pi, what will happen? The supply is on, my VO, as the SCR is triggered at omega t equals to alpha, so my VO is equals to Vs, my Vd is equals to minus of Vs, Vd is equals to minus of Vs, and my what? As my Vd is minus of Vs, obviously my ID will be 0, because diode will be off. Diode will be okay. Diode will be off, and my Is equals to It equals to IO equals to what? Equals simply some constant, because I've assumed that my L by R is very large, L by R is very high than the time period of the waveform. Okay, this is my assumption. So obviously I will assume, like, here what is happening, inductor is energizing but by a very low amount, so IL is increasing but by a very low amount, all these things, right? Then at pi plus, again this will turn off and this will turn on, so my Vd will be basically equals to 0, right? Why? Because due to the inductor, okay, it turns this freewheeling diode on, and as soon as the freewheeling diode turns on, my VO becomes 0, okay, and my IO is equals to some constant value, because inductor discharges by a very low amount. But in this region, my, right, this IO is equals to ID, but my IS equals to IT equals to 0 amperes, okay. Is equals to IT equals to 0 amperes. So previously here ID was 0, and in the previous case, right, I forgot to write here that in this region, right, IO of t equals to my ID of t, but my IS equals to IT equals to 0 amperes. Okay, IS equals to IT equals to 0 amperes. So these are the currents. So now if we go and analyze this in the waveform, okay, what will happen? I have assumed my current is constant, right? I have assumed my current is constant. So in this region, right, my SCR is on from this alpha, this is the alpha, from alpha to pi. Then after pi, what is happening? Inductor is turning the freewheeling diode on and turning the SCR off. Okay, why does it do so? Because if the inductor, right, if the inductor is keeping the SCR on, then it has to supply power to the source and the resistor. But if the inductor only keeps the freewheeling diode on, it has to only supply power to the resistor. So it will want that. It does not want to change its state by much. It does not want to reduce its energy by much. It wants to store it, right? It wants to keep it. So it sees that, okay, if I turn on the freewheeling diode, what is happening is that I am losing less amount of energy, so I will turn on the freewheeling diode. Obviously, there are equations involved here. I'm just simplifying the things here. So I'm just telling you the story, but actually, like, there are equations, mathematical equations, all those things are here. For simplicity, I'm explaining this in terms of a story. So in this region, SCR is on, in this region, SCR is off, and as soon as the SCR is off, the freewheeling diode will turn off. So this is the output voltage waveform. So when the SCR is on, right, the output voltage will follow the input voltage. VO will be equals to VS. Whenever the SCR is off, the output voltage will be 0. Why? Because diode has turned on and diode is directly connected across the load. It is a anti-parallel diode, right? Then again SCR turns on and this cycle repeats. What is the thyristor voltage? SCR voltage. So from 0 to alpha, it is in the forward blocking zone, and from alpha to pi, it is totally on, so it will be 0. From pi to 2 pi, what will happen? It will be negative. Okay, it will be negative. Hence, it will totally be in the reverse blocking mode. That is, it will be in the it will follow the input basically. Vt will be equals to VO. Okay. So here I forgot to write that whenever this is off, right? Whenever this is off, this Vt is equals to VO. So here VO equals to minus Vs, and then diode turns on, and as soon as this diode voltage is 0, so Vs equals to Vt. So basically it is negative because Vs in this region is negative. Okay. Then what is the diode voltage? So diode voltage will be simply, it will turn on when the SCR is off. So when is the SCR off? Here, right, in this region. So from alpha to this, from pi to 2 pi plus alpha, diode is on and SCR is off. And from 2 pi plus alpha to this 3 pi, SCR is on, diode will be off, and it will be reverse bias. Obviously, it will be reverse bias. This time diode voltage will be equals to the supply voltage, and negative of the supply voltage. And although the supply voltage is positive, but as it is negative of the supply voltage, so diode voltage will be negative, and hence it will be off. Now, what are the waveforms? What are the current waveforms now? What are the current waveforms for different cases? Case 1 is my 4 tau, right, settling time is just greater than pi plus alpha by omega. Basically, this is the discharge time, right? Discharge time. So if it is just greater, what will happen? I will see ripples here. So these are what ripples. I have explained this in my filters lectures as well. These are ripples, because like my current is confined between some value. The continuity has improved by very much because it is charging, then again discharging, This is like exponential charging, exponential discharging. And IT and IO, ID, I have already drawn here, so you can understand. But if my current is constant, that means my time constant is very, very high than the discharge time. So we can't see the discharge. Okay, it discharges by this amount, this tiny amount, but I cannot see it. I cannot feel it. It will discharge, but by a very, very tiny amount. Okay, which is not much of a issue to us. Okay, it's not much of a problem to us. So it will be almost constant. Okay, so this current, right? This IO, this is the IO waveform, current waveform. This will be constant. So whenever the time constant is very, very large, this will be always constant. Okay, so this is my IO waveform. Okay, so yeah, that is the case. Now thyristor, like whenever the SCR is on, thyristor will carry that constant current. Whenever the diode is on, diode will carry that constant current, so it will be almost same. Now what are the equations? This is the most, like, people fear from this, but this is actually the easier to analyze than the other cases. Why? Because here all the expression becomes simpler, because the output voltage will be 0 from pi to 2 pi plus alpha. It will be only equals to Vs from alpha to pi. Okay, so in overall a cycle from alpha to 2 pi plus alpha, only it is equals to Vs from alpha to pi, else it is 0. Okay, my VO average will be simply Vm by 2 pi 1 plus cos alpha. IO average I can derive from that. Then average load current. Load current I have already derived. If VO is constant, right? One thing you should know: even if VO is constant, IO, that doesn't mean if my current is constant, that doesn't mean that my output voltage will also be constant. Okay, so what do I mean by this? So if my, let's say, current is constant means that this L by R is very, very large, but VO, right, output voltage waveform is not constant, because output voltage is defined by the supply, okay, and the freewheeling diode, not from the L by R, not from the load. Okay, so output voltage will not be constant. So this is what I meant by this statement. Even if my, I'll just write it. So here I will write in words, even if my load current is constant, because I want both of them constant. For that we use high, what to say, like, not, we use full wave rectifiers and then 3-phase rectifiers, all those things we use. So even if my load current is constant, output voltage is not constant. Okay, so this is one point I wanted to mention. And if my load current is constant, right, then what can I say? I can say that load average current will be equals to RMS current will be equals to maximum current, because if load current is constant, it is just a simple DC value, right? So obviously the RMS value is this IO average only, the average value is this IO average only, the the current, right, the overall maximum current will also be equals to IO average, because it is constant, it is never changing. Now RMS output voltage. So RMS output voltage we can derive here, because it is easier. It is simply only the, like, supply voltage equals to, else it is 0, otherwise it is 0. So we can integrate it, and like in the notes I will write down the derivation here. In the notes I will write down the derivation and you can derive it. We have derived it previously also, but in the notes here I will write down the derivation. Now what about the load power? So load power, right? Load power, as everything is orthogonal, I can write it in terms of sum. Okay, so load power is summation of the three things, that it is the resistance power, it is the inductance power, and it is the battery power. So obviously this inductance in a cycle will not take any power. Okay, it will take some energy and it will give out some energy, and that will be equal. Hence overall average power of the inductor will be 0. But what about the other things? So overall output power, right? Overall output power will be simply equals to, what is PR? PR is simply this IO RMS whole square into R plus E into IO average. Okay. Now one important point to note here is that if only, like, this is always true, but if my IO is constant, then I can further simplify it. If my IO is constant, then what can I do is, I can further simplify that my PO will be equals to what? IO RMS, I can write it as IO average whole square into R plus E into IO average. Now what else can I write? So I will take common IO average, right? I will take it common IO average. This will be equals to IO average into R plus E. What is this? Can you tell me what is this? This is simply what? I have written it over here. Simply VO average, right? Like if I take the average here, like VL average will be 0, VO average will be equals to IO average into R into EA, right? So I can further derive this. My PO equals to VO average into IO average. Okay, this is my PO. So like this is the what this means, my load is DC because I derived it that whenever your power output power comes as expression like this, that it is VO average into IO average, then my load is DC, purely DC load. Okay, because the current is constant. So like what is the advantage? That this is equals to my PDC as well. Okay, this is the DC power as well. So my PO equals to PDC. So I will say this is this, not DC load, sorry, not DC load, I mean DC power, right? DC power. So whatever power I am getting, right, that is totally DC power, that is totally DC. So here at the converter efficiency, if my load current is constant, it will be PO DC upon PO. It will be simply equals to 1. Okay, simply equals to 1. If IO is constant, because IO average and IO RMS will be same, so all this will cancel each other out. Okay, so like what about the supply, right? Supply will have an interesting component. So this will have this currents like this, right? It will be positive and it will be like this. So supply current I can write with a very neat formula. If you have studied signals and systems, you will know that Vs I can write Vm, like this will not change, IS average will not be equals to IO average. Why? Because during the first half cycle, the thyristor current, the supply current and the load current are the same. But during the second half cycle, the thyristor current and the supply current are same, but the load current is equals to the freewheeling diode current. Okay, so load current is not always equal to supply current. So this time I cannot say that IS average and IO average will be same. In the previous cases I have always said that IS average and IO average are same, but here I cannot specifically say it. Okay, so what is my IT average? What is my IT average or IS average? Because IT average and IT and IS will always be equal to each other because they are in series. So this, right, this will be simply IO by 2 pi into pi minus alpha. Why? Because only for this area, that is pi minus alpha, IO is like IO is equal to that constant value. If my like this analysis, right, is done keeping in mind that my load current is constant. So if you simply like find out the area, this is IO, right? This is some constant value IO into pi minus alpha divided by the time period, that is 2 pi. Total time, like repeating time period is 2 pi. So I'm getting this. Now RMS, right? RMS, there is a simple formula. Like again, this area gets under root. So pi minus alpha into 2 pi. I have to take the under root and I have to multiply the constant number. This is what we learn in signal system. If you couldn't understand this, go through signals and system, and in my complex power chapter as well, I have explained about this a bit, right? In RMS and all those things, I have explained about this. So you can go through and watch that again. Okay. So and power factor will be again same formula, PS upon SS, PO upon SS. So PO, right? If load current is constant, what I can write is that it will be IO into IO average into VO average. But I cannot simply cancel this IO average and this IS RMS, right? They are not equal. And this will be VS RMS into IS RMS. And what is IS RMS? IS RMS is this value, right? IS RMS is this value. It is in terms of I2, so I can replace this. Then I can do the computation. So these types of sum will do in full wave rectifiers, not in half wave, because they don't generally ask questions from half rectifiers. Mathematical ones, at least conceptual, they can ask, but mathematical they don't ask. Okay. So this is the analysis basically about the full wave half wave rectifier with RLE load, right? And like for the freewheeling diode, what will be the currents? For the freewheeling diode, the currents will be something like this. Just the opposite, right? Just the opposite, because for how much time it is conducting? 2 pi plus alpha minus pi. It is pi plus alpha, and what is the area? IO into 2 pi plus alpha minus pi. That is the area divided by the total time period. That is the 2 pi. So obviously this will be the average diode current, freewheeling diode current. Okay, and RMS, again I take the under root of this, that will give me the RMS. This is some formula, not formula, this is a trick that we use in signals and system, and you can learn from complex power as well. So RMS is very easy. So whenever the load current is constant, finding RMS, average, all these things are very simple. Okay, not that difficult. So like these are a few parameters. So conduction period is basically T on is pi minus alpha by omega. This is the time for which the SCR is turning on. Natural commutation period is again pi by omega, because the inductor is naturally commutating it just at omega equals to pi plus, and from pi plus to 2 pi, SCR is always in the reverse blocking mode, so it is off. Now what is the peak inverse voltage of the thyristor? So I have to do it from pi plus to 2 pi, the SCR is always off. So SCR in the reverse direction, it will be Vm. Okay, and like it will always get Vm voltage. It doesn't matter, right? Doesn't matter. So it will always come across Vm voltage. And for peak inverse voltage for forward for freewheeling diode will be what? So freewheeling diode, right? If my alpha, like these are also two functions. If my alpha is between 0 to pi by 2, if my alpha is between 0 to pi by 2, this will be the value, and if my, not this, it will be simply Vm, right? No, this will be the value, sorry, this will be the value. I will explain just in a bit. And if my alpha is between pi by 2 to pi, this will be the value. Let's go to the graphs now. So if I go to the graphs, I will be able to explain what do I mean by this particular equation. So I will take this with me as well. Okay, where did it go? Yeah, here, right? So we'll just quickly take this, copy here. I will paste this and make this smaller. Okay, change the color. Now let's say if my alpha is lying between 0 to pi by 2. If my alpha is lying between 0 to pi by 2, what is happening? I am lying between this region, right? This region. So my SCR is turning on before, like this is reaching maximum peak voltage. So as soon as the SCR turns on, what will happen? The diode will have to block the whole voltage, because the voltage across the SCR will become 0 now. So diode will block the whole voltage, and for the diode it is a reverse bias voltage, right? It is negative voltage. Even though supply is positive, but it is minus of Vs, so it will be negative. So as soon as alpha is lying between pi by 2 to 0, so what will happen is that diode has to block voltage, and as alpha is between 0 to pi by 2, this voltage, right, will go across this negative peak voltage as well. This voltage will go across this negative peak voltage as well. Then what will happen? Then basically I can say that diode has to block the maximum peak voltage. So that's why if my alpha is between 0 to pi by 2, I have written it wrong, it will be Vm. It will be Vm, right? Okay, that's why I was getting confused. It will be Vm. Now, if my alpha is between pi by 2 to pi, if my alpha is between pi by 2 to pi, so I am lying in this region, right? So my like pi by 2 is here, and my alpha is lying in this region. So my SCR is blocking the most of the voltage, because SCR will block until here. Then again suddenly it will not block, it will turn on, and the whole voltage has to be blocked by the diode. But this time, right, I have already passed the menaces Vm, right? The Vm, like I am already reducing from the Vm, so the maximum voltage that will come across the diode will be this voltage. What is this voltage? This is Vm sine alpha, minus of Vm sine alpha, right? Although like we are talking about peak inverse voltage, that's why this will be positive only. So this will be Vm sine alpha. So that's why if I'm lying in this region, right, in this region, then the peak inverse voltage will be Vm sine alpha. If my alpha is lying in this region 0 to pi by 2, then my peak inverse voltage will be Vm. I hope you understood graphically how did that happen. Okay, so I will just make this correct. Okay, rectify this. So this will be Vm sine alpha, and I will just reduce the size. Okay, now let's come to the next key point, that is this. If my VO average is greater than Vm by 2 pi 1 plus alpha, this result is what? This result is with freewheeling diode and constant load current. Okay, or continuous conduction, constant load current. Okay, so now then what I can say is that then the load, like if this is greater, right, if my like calculated VO average is greater than this, then I can surely say that load current will be discontinuous and load will be RLE. Why? Because what will happen? The VO average is more. That means for some period the waveform will be something like this. this is omega t, this is VO, and I can draw this in a different manner. This will be E. This will be Vm, right? So if, let's say, if this E was not present, okay, then what I could have said, that SCR is always on. SCR is always on, right? So this, if this E can only come, my output voltage, in the output voltage expression, E can only come when the load current is 0. Whenever the load current is 0, then only this E can come. You just recall, if my SCR is on, this E value, right, can never come. It will be totally equals to, VO will be equals to, so I will, let's write down the cases. I'll just write down the cases. Here, I'll just reduce this. If my SCR is on, then what happens to the output voltage? It is VO equals to VS. If my freewheeling diode is on, okay, then my output voltage is simply equals to 0. It can not be positive. So in this whole thing, right, the maximum output voltage with this combination will be this value, okay, that is the maximum output voltage, and my IO in both of these cases, IO will be greater than 0. IO will be positive because either freewheeling diode is conducting or SCR is conducting, and they are unidirectional devices, so current can only conduct in one direction. Okay, next, what can I say? If both SCR and freewheeling diode is off, okay, both, like here, right, in one case freewheeling diode is off, in this case like SCR is off, but if both are off, then my output voltage is what? VO is equals to E, and then only it is possible that the average output voltage increases, because E is some positive value, it will only increase the area, right? It will only increase the area. That's why whenever I see something like this, that VO average is greater than this possible value, this value, okay, this very special value, then I can say surely that the load current will be discontinuous and load will be RLE load. Okay, so these are intuitive things. So even if you couldn't understand, don't worry. Okay, you can skip this part. Okay, if you couldn't understand, that's fine. That's totally fine. Now I will give these questions, few of these questions as homework, and in the next lecture we'll solve all these questions, and we'll also solve with half a rectifier with capacitive load. So this is the first question. You can take the screenshots. Second one, okay, third, fourth, fifth. Like this is with the capacitive load, right? No, not capacitive. This is simply RLE load, and but just few things are different. And sixth, I think there are a few more. So okay, this is not this, and I think yeah, this is this, and we'll do a lot of questions in the next lecture. And this is the last one. I believe after that we don't have any question. Okay, so yeah, this is the last one, and in the next lecture we'll study about capacitive load as well. Okay, so thank you for watching, and I will see you in the next lecture. If you couldn't understand like whatever I explained, right, this is a bit difficult lecture, so you can rewatch it again. Okay, thank you, and I will see you in the next lecture.